the bottom figured out, right? Since we just went through that.
Yes.
Yeah, we're good there.
But top still have.
So originally we had the top and couldn't figure out how to make the bottom work with that configuration.
Yeah.
And then now we have the bottom figured out, but we can't figure out how to make the top work.
To align them or just work?
Yes.
To align.
No.
No.
We had it initially.
Like-
we just couldn't align.
Like the which nodes were which input,
Uh-huh.
right?
Uh-huh.
We had to change that in order to get the bottom to work.
Yes.
And now we can't figure out how to get the top to work with the new configuration.
Functional or just the order of the alignment?
Order of the original.
Okay, that's probably sometimes you couldn't figure that out at all. That's
So you
if it
can't,
couldn't, that's
like,
not required.
crisscross lines?
Yeah, you just have to introduce metal one probably.
Okay.
You're just not supposed.
Yeah, yeah. Yeah, let's see. I don't know. Let's take a look. I am not sure if that's the case. All right. Let's see. So AND logic, OR logic, right? OR logic are in series, and parallel. So you are getting. Oh. Just one here. And we decided to do one first. And then A, B are in parallel. So if we put E to the bottom, it wouldn't work at all. So don't do that. Yeah, just give you guys some easier time. Okay, just let you guys know. I have to put this on the top. And let me see, if I go through this, I'll probably just let you guys know the solution to it already. A, B, C, D, E, right? A, B, C, D, E in that case. So I think the bottom one is more difficult to do, so let's just do this first. If we keep this as a E, and do this, right? So this has to be E, A, B,
The outside.
these two, C, D, like this. So for the top, it's basically 3 branches in parallel. I want to keep this guy to be E. So if I do this, no, that wouldn't work. 3 branches in parallel. So 3 branches, we need this structure, right? Right? So
No, You
Hmm?
heard that right? That's how you,
Was these two?
yeah,
That's how I do.
that's how I do it.
That's how I do it too.
Yeah, couldn't you connect the N two and then do it through
Yes. Hmm?
Yeah, that's what we.
Yeah.
Was that Zach? What do you say?
That's what I said there.
So if that is E, these,
Those have to be A and B.
yeah, A and so that has to be A and B. Yeah, but here you have to split it, so that's why you cannot really align them really well, right?
Yeah.
Yeah, which is fine. I mean, a lot of times you couldn't. There's just no way to align them.
Cool.
Yeah.
Oh, so they're not going to be aligned well.
No.
Is there a way you can kind of like know that ahead of time? Or do you need to kind of,
Oh, theory behind it?
right, do you need to kind of exhaust all your options?
Yeah.
Just brute force it until you realize like, oh,
I hope
It's-
AI can help.
I just wasted 25 hours working different directions
know,
of this
yeah.
75 node transistor circuit.
Oh, it wouldn't be 75. These are just the individual gates. You are going to reuse the gates. We are building smaller gates. Larger scale circuits has to be synthesized by tools, by Cadence.
Yeah.
There's no way that it can optimize it by hand, I think. Unless you want to spend time on it, just keep working on it. But still won't be really optimized, I think. No.
Okay.
And if you go to the company, work for the company, there's for analog circuit design companies, if you are designing the individual blocks, you probably will work on these ones. But for most of the companies, you don't even touch this bottom level circuit design. You just use everything ready, put in boxes by TSMC. So you use a commercial, it's called standard cell library. The standard cell library. So these libraries already includes schematics and layouts. It's already there. And then you load the library to your design. And you remember the schematic, because all these are in AND logic and then ORed. So it's basically 3 in series, 3 parallel transistors in series. You can look at your notes. We already have the AOI schematic drew there on Friday. Okay, no problem on this. And we were talking about the PMOSes. And remember, for these in parallel, we were able to find a solution, which is this. And the reason we want to keep all the traces, no matter one trace on the top, is because we have to introduce the trace from this node as an output and to interface to the NMOSes. Okay, and this is simple because it's 3 branches. We know the three in parallel, right? It looks like this. So the only difference is we have 2 in series instead of just 1. Okay. Then we have this and this. Okay, I don't think we can align this as well. Align the PMOS and NMOS in the example as well, because this structure has to split all the transistors on 2 sides. So I don't think you will be able to align them here. But still better than not using stick diagrams. Just randomly laying out everything will take a lot of space. Okay, that's method 1. So the reason I want to talk about this example is because you can simplify this logic and create a different circuit, which may give you a different results, different number of transistors. Let's see. So this one, so combine these two terms. It gives you a different logic expression, which will result in a different layout, definitely. Okay, if we decide to do this first for the PMOS, and then this one, it's unlogic OR, so this will be two PMOS in series, and in parallel with this guy, we're expecting something like this. A, B, C. And this, think about the NAND gate. This is just a parallel resistor. So done with the PMOSes. For NMOSes, this is the chicken leg, A and B. Another chicken leg, but with two in parallel first. And then the last one. One, two, three, four, five. So two in parallel and then two in parallel. So first, two in parallel is pretty simple. I just have two in series instead of one. If I do this, I can easily figure that out. And then another two in parallel, we can do this, so introduce the output from the middle. This one is a little bit challenging. See if you guys can figure that out. I'll give you 1 minute to think about it. So if you look at the structure, this node is being split into 3 branches. So you want to use that 3-branch method. But the thing is, eventually you need one more here at the output, and this node doesn't share anything with this node. So that's why it's challenging. So if you introduce this guy like here, if I do this, and I'm trying to do this, right? Because I know this is 3 in the branches looks like this, right? Looks like this, right? This structure. So I'm doing this. Then what's the problem? So if I do this here, which means I'm putting these two in parallel here first, and then I'm trying to, have these two in parallel. So this one has 3 branches, right? 1, 2, and 3. Yeah? So it forms the 3 branches, which is fine. So that works. So what is not working? The 3 branches has the output. So it's basically shorting these 2, right? Which it shouldn't.
Yeah, it should do.
So this doesn't work. PMOS is fine. What else we can do?
We could start with C and B, but
C and B?
yeah, start from ground basically.
Oh, start from ground, okay. From C.
Yeah.
Then, so 2.
Yeah. Should need 2 connections.
So 2, like this. Oh, this.
I think so. Maybe.
From ground, you got a C here, and you got an A and B here. But you got these 2 shorted again. So it's shorting here, but it shouldn't. So this doesn't work as well. One, 2, 3 branches, and you don't want to short the output because the output here for the 2 is here, and the output of these 2 is here, and they are not shorted, so you don't want to short them
Yeah.
because the output of these 2 parallel transistor is here. It's being sent to an individual transistor somewhere else. So what you can do? You don't want to short it here.
Go to the very end.
If you do this, so the output here goes to this transistor, which is C, and it's going to merge with the output of these 2 series transistors over here, and that becomes ground. Make sense?
Oh, because then. Settings?
Hmm. Yeah.
So, that last transistor would be C,
Yes.
and the 2 on the far right are B and A, right?
Mm-hmm.
And
That's another A and B.
I guess since the other 2 are in parallel, it doesn't matter.
Hmm? So these are in parallel, right? As if that the order doesn't matter here, and these are. And you're thinking that these are the same signal lines, right? Same signal lines.
Yeah.
We don't have to worry about that because same signal lines. We just short them to the. Can you reduce number of transistors because they have the same signal to the gate?
Did you reduce it by 1? No.
I don't think so.
No, because they're different. Yeah, because
Even though they are shorted, right? But they are still individual transistors. It controls all the transistors. Controls that to form this logic. If you remove them, then you are changing the logic. I shouldn't change the logic, right? So very quick recap on the quizzes that I didn't cover last time, really quick. So I went through these two problems, I didn't do this one. So surprisingly, several of you guys didn't make it right. So inverter linear input, you definitely should see something like this, right? Okay? If you drew it something like some other patterns, it's not unacceptable, because inverters linear input output, we did this for several times, including the labs and everything. So make sure you know this curve, okay? And you can see this curve is holding on for a longer time, or for more voltage input. So this definitely has a stronger PMOS. Okay? And this guy is not able to hold a zero state for too much, but this guy can, so this is a stronger NMOS. Just let you guys know, okay? Very quick recap on this. And I think we have some questions here as well. So most of you made it right, but make sure that make sure it's non-gay, and and when you drew it, you made the certain connections. There are only two inputs. Okay, that's first thing. And for layouts, you have all the solutions from the notes, right? You don't really need my solution here.
Yeah.
Make sure you drew everything right. Okay, output. And label them A, B, A, B, whatever. Okay? That's the solution for the quiz. And let's look at the lab tomorrow.
Are we doing adders?
Adders, yes. Hope we still have time. Sorry about that. That's what I'm talking about, because we have adders in the lab. All right. So non-gaze, NOR gaze layout, no problem. And when you are drawing the shape of it, make sure that you press Y, right? So grab a shape and press Y to modify it. It's not a really CAD tool, doesn't like AutoCAD or something else. This is not very perfect, but you can still create the correct shape. Make sure they are in a reasonable ratio here. As this is bigger, as the bubble is smaller. You don't want to draw a super big bubble here. I'm going to take points off if you guys see that. So you know what the gates look like, right? So you guys are junior seniors. You know what they look like. And so this is the XOR gate over here. The schematic is already given, and you verify the logic. So I'm trying to talk about. Wait, okay. So here's a either circuit with individual gates, okay, and the yellow color is metal strip, since you have a lot of circuits in the middle. And so one thing I want to let you guys know is this schematic came from a logic derivation. I think we already did that for many times in embedded or in logic. So here's the circuit. I'm gonna write down the logic really quick, and then you verify it using simulations. So this was not a very good presentation because this is overlapping with the frame of the display. So it's actually the pulse is over here. Okay, that's going 0, and then so why I can tell, because you can see the pulse function has a 10 nanosecond delay. The signal A has a 10 nanosecond delay, so it waits for 10 nanoseconds and then start 5. I guess doing this. So you can see this is a Flatter's logic because it's A plus B, and it's giving you S as a summation and the carry out. So you have to verify it using pulses. And eventually the layout of the PMOS, one thing I didn't do, but you guys should do, is I think this was a long time ago I laid it out and they ignored that unwell. So you can see these are the unweld tabs over here on the top, right? So I'm shorting them, all of them to metal. But another thing is a better practice is that after you laid out all the PMOSes, you should cover everything with unweld over here, just one single unweld. And another thing is for the unmoses and all these P tabs, you want to cover it with a pure unweld, a P weld, right? For the unmoses and the P tabs. So in that case, you need to separate the unweld and P weld clearly. But you can see here, I don't think I did a good job because you can see here, I think I was trying to do it, I was trying to align it, and I think they are mostly aligned. But you can see this P weld is lower than this P weld, so if I'm trying to cover the whole thing with a one P weld, it's going to overlap with this unweld, and that wouldn't work. Just let you guys know, you want to separate the top, so the PMOSes and unweld, you want to draw a box and cover all the PMOSes on the top. And for the unmoses, you want to cover everything to the bottom with one P weld, right? And you want to separate them clearly. So align them in a certain row, right? Don't have up and down like that. So we want to plan them ahead of time. So this guy has more stuff in the middle, and these ones don't, because these are simple ether gates. So you want to make them longer, like taller, so you can fit this shape into this one so they have the same height. Remember, all these cells are in the same row, so that is why you want to keep them the same height, so you can align them with the same height and measure them, right? So before you start laying out too many things, you want to, really do a measurement and have a plan. So that's one thing for that. So you can see, we'll do this, but we're not doing any calculation and derivation for that for tomorrow.